Exam question revision video for GCSE Pythagoras. So the question, we're given a right angled triangle with two of the lengths and we have to calculate the length of the other side, and our thinking here is we know the lengths of two sides of a right angled triangle and we're required to find the length of the third side, and the diagram is not to scale, meaning we can't measure it to find the answer. What we can use is Pythagoras' theorem. The side whose length we need to find is the long side of the triangle, so it's important we get the theorem the right way around. And Pythagoras' theorem states that the square of the longest side of a right angled triangle is equal to the sum of the squares of the two shorter sides. And you may have learnt it as a squared equals b squared plus c squared, or a squared plus b squared equals c squared, but the advantage of this way of remembering it is that you make sure that you get the longest side squared on its own, and it will then work properly. So the longest side in this triangle is QR, so we have QR squared, and that must equal PQ squared plus RP squared, and those two are the shorter sides. So all we have to do is pop the numbers in for PQ and RP, 1.41 and 0.89. We square them and add them, and we can enter that exact expression on the calculator, and that gives us exactly, in this case, 2.7802. Because this is exact, I would write down all the digits. In another question, if it had a lot more numbers after the decimal point, then make sure you keep enough significant figures to allow for the next calculation, so one or two more than the number of decimal places you want in the answer. And that's QR squared, so we need to square root both sides. QR squared becomes QR, obviously, and then we're looking for the square root of 2.7802, so on your calculator you could do square root ants, and that comes to 1.67 in meters. And notice we're keeping the same number of decimal places as the numbers that are given in the question. So the numbers in the question 0.89, 1.41, so that's 2 decimal places, so we give the answer to the same number of decimal places. Okay, an alternative question using basically the same maths could be this. So we have a diagram not to scale showing a frame made from a wire in the shape of a rectangle with supporting diagonal struts. Find the minimum length in centimetres of wire required to make the frame and supporting struts. So our thinking here is that we know all the sides of the rectangle. It says it's a rectangle, so that means that BC is the same as AD and CD is the same as AB. And the diagonals can be found using Pythagoras as in the main question. So once we've done that calculation, then all we would do is add up all the lengths. And then finally we've got to be careful because it does specify the minimum length in centimetres, so we must make sure we convert to that at the end because the lengths given are in meters. Okay, so for the rectangle itself we have two lots of 0.89, those are the two sides, and 2 times 1.41, that's the top and bottom, and they come to 4.6. For the cross members we have two lots of the answer we've calculated previously. I'm not going to write all that out again, but obviously you would if you were answering this question. So that's two lots of the root 2.7802, and that is a Greek letter capital S or sigma, that means the sum. So I'm saving bother as mathematicians tend to do. So the sum, which means the whole answer, is going to be our 4.6 plus 2 times the square root of 2.7802, and the reason I've left that as a square root is in case that when doubling it might change the decimal places, so I'm keeping the accuracy going as long as I can. And in fact when you enter that into the calculator you get 7.93 meters, and of course we have to convert that into centimeters. There are 100 centimeters in a meter, so we times by 100, which means bouncing the decimal point along 2 places, to the right, which gives us 793 centimetres. Now the bonus material here is a proof of Pythagoras' theorem. You're unlikely to be asked this in the exam, although they could give you some steps and ask you to fill them in, something like that, but it's something that you might have seen, but if you haven't, it's rather lovely. And it will help with your general mathematical thinking towards the exam. So there are techniques in here which are useful. So what we've done is we have a square, which we've put in a square inside, and the area of the large square must equal the sum of the areas of the smaller square and the four triangles. And notice those four triangles are all similar. They've all got sides of A and B, and they all have a right angle in the corner because we've stated this is in fact a square. So let's see what happens. Well, we've got four triangles plus the green square, which I've denoted by a square at an angle like that, and that must equal the area of the whole shape. The triangles, each of them has sides of A and B. The sides are at right angles, and so B can be thought of as the height, and so that's just the half times the base A times the height B. They're all the same, so we have four of them. And then of course the green square is just C squared. The sides are C, so it's C times C. And for the whole shape we've got a big square, and each side of that is A plus B. So its area must be A plus B squared. Okay, we can tidy up a little bit. 4 times a half is 2, so the 4 times a half AB becomes 2AB plus the C squared. And then we need to open this bracket out, and you will or may have seen before that A plus B squared comes to A squared plus 2AB plus B squared. If you're unsure about that, then have a go at writing the brackets A plus B brackets A plus B, and then multiplying all four terms using FOIL or some other technique, and you'll find that it does come to A squared plus 2AB plus B squared. And then you'll notice we have 2AB on both sides, so we can subtract that from both sides, and that leaves us with C squared equals A squared plus B squared. And that proves Pythagoras' theorem. And then a final little thing, we're going to use that shape to show Pythagoras' theorem geometrically. So have a look at this little clip. And so what we're doing is we're sliding the four triangles and repositioning them, so we can see them repositioning like that, and then we can see that in the top right we have a square which is B squared, and in the bottom left we have an A squared. So if we label the four triangles on the initial one, we've seen them slide into place, but it's useful just having a look at where they all go. So number 1 goes there, number 2 goes down there, number 3 down there, and number 4 up there. But what we can see is that these two squares both have sides of A plus B, and so they're the same area, and each of them is made up as four triangles. On the left hand side it's four triangles plus C squared, on the right hand side it's four triangles plus A squared plus B squared. So what we have is that for the green square we've got triangle 1 plus 2 plus 3 plus 4 plus C squared, and for the red one we have 1 plus 2 plus 3 plus 4 plus A squared plus B squared, and we can subtract all those little triangles, leaving us with C squared equals A squared plus B squared. So that's quite lovely.